Hello everyone. Welcome to the dendrotools workshop, which is organized in the scope of TRACE 2021 meeting. Before we go to the details and to the organizational matters, I would like to ask the president of Association for Tree-Ring Research, Ute Sass-Klassen, to say some welcome words to all participants.
Yes, thanks a lot, Journey. Very nice to be here and to get the chance to say hello to all of you. And they are coming in, still people coming in, great. This workshop is an ATR supported event, and that means that we have from the ATR we have the policy to ask our very active members like Journey to provide us and also young research experienced researchers with the chance to join a workshop where they present with their expertise hot topics and important topics. Now this is one of the very good examples here because many of us are interested in the methods of the dendrotools and Journey, great that you agreed to give this workshop. We are very happy with that. And normally we also support these kind of workshops, which are normally happening live with the ATR traveling grants for our student members. And so that is not necessary today, because we are all meeting online here, but originally this workshop was supposed to take place in Lund in Sweden, where we have our TRACE conference, which will start tomorrow and also take place on Thursday. So many of you probably signed in for the TRACE conference. So I will see you tomorrow again in the conference where we have lots of interesting presentations across the entire amplitude of tree-ring research. So normally we should meet live, and that would have been 20 to 30, I think, Journey, participants 20. Of this workshop. And so obviously there is one big advantage of this situation now, because there's a lot more people have signed in for this workshop and can join and profit from this workshop now. So this shows the huge possibility of having virtual meetings, and we are really happy about that. Okay. I wish you a very successful meeting today. Journey will guide you throughout the dendrotools, and I hope to see some of you tomorrow, like I said, in the TRACE 2021. And I'm sure that I will see probably some of you next year in the TRACE 2022, which will take place in Germany. And I hope that by then you all use these fancy dendrotools today to prepare your presentation, to upgrade your research using these tools. And I'm looking forward to see you all next year then in the TRACE meeting, hopefully live in Germany with a live, maybe a successive dendrotools workshop. And for now, I wish you an inspiring workshop. And thanks again, Journey, for doing this.
Thank you very much, Ute. Thank you. Okay, so next, I would like to welcome my co-assistant and co-host today, Diogo Pavao, who is my friend, and we work on several common research ideas. So thank you very much, Diogo, for assisting me here and to agree to co-host this meeting. So Diogo will take care about the technical details, and he will also help me with the chat and answer any questions. So thank you very much, Diogo. Okay, now what is the schedule for today? So the workshop is planned to last approximately 3 hours, but then I will open the stage and you can join me and we can discuss some open questions. And if you have some troubles with the dendrotools, maybe you have tried it before. But anyway, in the meantime, during the presentation, you are invited to raise hand or to write anything in the chat. So if there will be any questions, any details, you can always interrupt me. So this is allowed as well, of course. So as you can see, the workshop is being recorded because we are later planning to put it online. So you can come back to the workshop and maybe do it again. Or also some participants who are not able to join today, who has maybe canceled, will also be able to see this workshop and benefit from it. So I think this is also possible later. Okay, so I think we can start if there are no questions. I believe you have all downloaded the workshop materials I have sent you through Dropbox or through question and through Dropbox and WeTransfer. You should have installed our studio if you're working in our studio, and I think we are ready. Okay, I have to close my Outlook.
Sorry, Erne, they're asking if you can present yourself a bit.
Oh, if I can, of course. Thank you very much. Yes, so my name is Jerne Jošenak, and I work at the Slovenian Forestry Institute. So I am, young doctorate. I finished my PhD in 2019. I am focused on research in various, in dendrochronology, dendroclimatology, and tree rings in general. But I also do research in forest inventory, in economic evaluation of forests. So at the institute, I have, let's say, a role of some kind of statistician or some kind of data scientist. So this is my usual working day. So I try to get a lot of experience with R and also other programming languages. Yes, this would be my very general introduction. So thanks. Okay, so I think now we are ready, and I will share you my screen with the presentation, and we can start. So, okay. Diogo, please let me know if you see the complete picture of PowerPoint. So it's nicely on the screen.
Yes, it is. Yes, perfect.
Okay. Excellent. So today's workshop is going to be mainly about the dendrotools app package, about the daily data, about the benefit of daily data in dendroclimatology, and we are also going to slightly touch the topic related to non-linear modeling, because my main topic in my PhD was actually non-linear modeling of the relationships between tree rings and climate. And this was also at the beginning the main idea of the dendrotools, but this topic related to daily data was actually kind of side effect of my PhD, but at the end got much more attention than the original topic, non-linear modeling. So we are today going to focus on daily data, but I would also like to say something about non-linear methods and in the non-linear machine learning methods, which are, in my opinion, also very beneficial in dendroclimatological studies. Yes. So we are first going to start with slightly more shadow images, and later when we are more aware of the content and about the benefit of the topic, we will get brighter pictures. So this is more symbolic for now. But the question at the beginning is, why should we consider daily data? Okay, so usually in dendroclimatology, we use monthly data. So this is the golden standard now. And if you think about, let's say, very classical analysis or very classical example, you have your tree ring chronology. And then you would like to analyze the effect of climate on your tree ring chronology. So you have 12 months, and you usually apply correlation analysis and compare individual months with your tree ring chronology and some seasonal aggregated months to see maybe the effect of summer or autumn, spring. So you have very limited options for analyzing this effect. But if you have daily data, then this window of opportunities, let's call it, it's much wider. So you can, for example, compare temperatures between June 15 and September 15 with your 3-ring chronology, or you can compare maybe narrower windows like 3 weeks, which are not possible using monthly data. So the very obvious answer to this question is, of course, but if you use daily data, then you have much more flexible insight. You get much more flexible insight into the dendroclimatological analysis. So, and one of the studies which I did in last years has shown that this so-called optimal climate signal, I will refer this to, so in dendroclimatological studies, we are interested in so-called optimal climate signal. Often it depends on the research question, but it means that we would like to see which climate variable, so which months or which seasons has the highest effect on 3 rings, right? So which explains the highest proportion of variance or similar. But this optimal climate signal almost never lies inside monthly boundaries. So usually, as you will see later, if we have the opportunity to slide our window using days, we will get better results. Okay, and another very important aspect of this research using daily data is that, again, very commonly, we are interested in stability of climate signal, which means that, for example, we identify that summer temperatures, June, July, August, have the highest correlation with our 3-ring chronology. And then we are interested how this correlation changes if we subset our years and maybe run running window and see what is the stability of climate from early period to late period, for example. But if we have daily data, we can also study what is the change of this optimal climate signal. Yes, so we can see maybe optimal climate signal is getting towards the end of growing season. Maybe it's getting towards the beginning of growing season. So we are going to do some exercises later. So keep this in mind when we get to the exercises. But I think this is one of the most important additional options for studies in dendroclimatology. Yes. So when I first time introduced the dendrotools R package and daily climate data, I remember now some students say, yes, this is great, great idea. Daily data is very promising, but there's no daily data, right? And I always say, yes, this is wrong. So all the monthly observations which we use today are based on daily data. So, but people just don't take a few hours to investigate, to find appropriate data set, which is based on daily observation. So now, as a first task of our workshop is to go through possible sources of daily data. So you can maybe mark this down, and when you will be looking for daily data for your site, it's you will be able to find it more easily. So I always start on Climate Explorer. So this is the link of Climate Explorer. I'm sure all of you have heard of this. So on Climate Explorer, you have two options. You can first search for daily observations from meteorological stations, like on the next slide, or you can search for gridded daily data. So there are many different initiatives, many different possibilities for download. You can see, so for example, there is EOPS. We will come back to EOPS later. Then Berkeley anomalies. Then we have some from Africa. So different fields, different gridded data, and you can already download some of the variables from this site. As I said, you can also go and search for meteorological observations, which means that you will have to enter or the name of the so maybe some city which is in nearby, like a station's name, or you can also enter the coordinates or even click on the map. So you will then get observations from exactly specific meteorological stations. So this is, yeah, on one side is beneficial because it's because those observations might be of higher quality, but the problem is that there is often a lot of missing data. Yes, so especially in Southern Europe or Eastern Europe, it's often the case that there is missing data, and then you have to yeah, you have to find a solution or workaround. So that's why I almost always use some kind of gridded data. As you will see, this is the EOPS gridded climate data set. And this is my favorite data set. So especially for Europe, I always apply it. And in my last 5 research papers, I always used EOPS because in my opinion, it's it has high resolution, also relatively high temporal coverage. It's updated regularly, so it's you can just download netcdf file, but then you need to do some some coding to get your coordinates out. But this is my favorite data set. There is also, it goes back to 1950, but if you would like to go back in time, this is an option. But I would say that you can use this only for regions which have known, let's say, yes, longer and reliable climate observations like Central Europe and Western Europe. So I wouldn't use this data set, for example, in the Balkan region, because I would say that the density of meteorological stations here before 1950 was relatively scarce. Okay, if we go on, so sometimes we are now working on one research where we need global gridded daily data. Okay, and I would like to mention this so-called CRU daily data set, which is also based on Japanese reanalysis and goes back in time, so back to 1900. It's 6 hourly time steps, so you can also calculate minimum and maximum temperature out of this. It's global and on 0.5 degrees regular grid, so you can download it here. But very important to mention that if you go before 1960, those data is mostly simulated using the Japanese reanalysis data. But if you go so from 60s till 2019, this data is based on actual observations and of course gridded. So I have tested this data set, and in my cases, it was very promising and reliable as well. So it has slightly lower resolution, but if you consider the global scale, it's very promising. Now, yeah, I would like to mention just a few further options. If
Sorry,
you would like.
you have one question.
Yes,
what about
please.
Quality of 0.1 as 0.25 EOPS?
So in EOPS, I always use 0.1. So because I believe this is more representative, and the difference between 0.1 and 0.25, I would say, is just based on the elevation behind this data. So these temperatures are pretty much based on elevation information. So I always use 0.1 because I think it's it's probably more representative to specific point. But if your research, if you are working in maybe lowlands without let's say difference in terrain, I guess 0.25 would also be okay. But I have never compared those two. I just focused on 0.1 because by default, I believe is better, but yes. So in the EOPS, you have minimum temperature, mean temperature, maximum temperature, and precipitation. I think maybe also radiation, I'm not sure. And you can also get the information about the elevation for each point, which is then very useful. Maybe you would like to interpolate so maybe you can extract more grids and then interpolate to specific site using exact coordinates. So this is also what we have done recently, and it works great. Okay, so back to further options. I would like to mention Joint Research Center, AgriForecast research portal. So we have used this data, but it's only, I think, since 1970. So it's only 50 years of data, but relatively high quality. Then ERA 5 hourly data on pressure levels from 1979 till present. This is Copernicus data set. And I think recently I received an email from Copernicus that they extended this back to 1950. So please, if you will use this data set, check this out. It's very neat because you can simply insert coordinates, and then you get so-called API. And if you copy this API in your Python, it automatically saves a CSV file of this data on your computer. So it's very convenient. Okay, Chelsea. So recently we worked with the data on the Azores with Diogo Pavao, and we have tested also Chelsea data set. Chelsea is very high resolution, I think 1 kilometer grid point. So it's when you need really high resolution data, I think Chelsea is very promising. And then, of course, NOAA data sets for North America. I have not tested anything for North America, but since this is a very developed part of the planet, I believe that there is a lot of gridded data sets. Finally, don't forget about your national meteorological agencies. When I worked on my master thesis, my site was relatively remote and the data set was relatively short. So I contacted our meteorological agency and asked about, is there anything I can do? And they invited me into the archive, and they gave me regional archive. So, not digital, but in text format. So, and asked me to digitalize this data, and I was able to extend my data for 20 additional years, so which is often very important to go back in time. So don't forget to ask if your meteorological agency, because a lot of data is available, but just it's not digitalized and it's not online. Okay. So that's all about different sources of data sets. We are now going to dendroTools RPEC. So I see there are some questions in chat. Diogo, can you please check this out? Okay, so I see we have answered this. Can you please, the question, and
I guess we answered everything, yeah.
Okay, so there is a question about the extension back in time of Chelsea. Diogo, maybe do you know this, because we use this, do you remember? I'm not sure.
Oh, now I see the question, yeah.
Yes.
The time series goes to 9050, I would say.
I also think it's 9050, yes.
Yeah.
So I think we have, yes, so it's 9050.
Yes.
But please check this.
Yes, I could just put the website on the chat.
Yes, that would be great. Diogo, thank you very much. Please put the link into the chat box, okay?
Yes, you have one more question. What about gaps with graded data?
Okay, so there is already the Raul. Thank you very much. Raul posted the link for Chelsea. Thanks. Sorry, Diogo, one more question.
Yes, what about gaps with graded data?
Oh, gaps. Well, at least what I have used so far, like EOPS, there are no gaps usually, I think. So I don't think there is, usually some data sets come with the additional data set with uncertainty. NA. So NA sometimes appear. Yeah. Okay. Yes. Okay. Now I see. So at least as I know. So in EOPS, they run the models to simulate gridded data. And they also run models which simulate the uncertainty, which means like, so if the uncertainty is too huge, too big, so there is no data and no methodological observations, I believe then they put NA instead of let's say, very unreliable estimate. So if you have NA in EOPS or any other gridded data sets, I think there is not much you can do. On how to deal with NA. Well, that might be that it really depends. So if you have just a few NAs, let's say, and they are single days, then you have option of maybe you can, for example, just see the previous and the next day, and you can put the average between previous and the next day. But if you have 1 month of missing values, then I don't think you can do much about this. Then again, it depends on the variable, because if you work with precipitation data, it's really difficult to interpolate precipitation data. But if you have temperature data, you might find methodological observations, maybe 100 kilometers away from, but they will still be, okay to estimate a few NAs. But in general, especially if this NA is present in gridded data, this is a problem, because scientists who are in charge to provide gridded data, if they estimated and they decided not to insert a value, then I would say it's difficult to find a better way than they did. Yes, so NAs are definitely more common in precipitation data, because it's also more difficult to measure precipitation. But again, I would suggest maybe if you then find the closest meteorological station and you compare overlapping days, and then you decide whether this overlap, and then if the explained variance between those two locations is okay. Otherwise, it's then just maybe find another data set, or or maybe reduce the number of years you are planning to analyze. Okay, maybe we can come back to these NA problems at the end of the workshop. Now we have to continue with the dendrotools. Okay, so in the next slides, I will slightly introduce the dendrotools R package, and then the function daily response, which is the core and primary function of the dendrotools R package. Okay, so dendrotools is available on CRAN, which means that it was checked by CRAN machines. So CRAN is a comprehensive R archive network, and all the packages which go on CRAN, they were checked that they work, so that they have all the proper documentation, and that they work on Linux, on Windows, on Mac, and other systems which exist. So if you go on CRAN, this is the link you can click, you will get to this site, and you get some basic information about the package. First, about the imports, which means that when you install dendrotools, all those packages will be installed on your computer as well. Then you get information about the GitHub. For example, if you find a problem, which also, of course, can happen, then the best way is to send me an email or simply write and describe the issue on the GitHub. So GitHub is a well-known developer page where people can exchange codes. And also, before you publish package on CRAN, you will likely publish it on GitHub. So yes, GitHub is very important for the R community. Next, you get information about dendrotools results. So CRAN always runs all the packages and tries to find some errors. And if there is an error, I immediately get notified and they ask me to remove this error as soon as possible. So if you click on the dendrotools PDF, you will get to the manual. So manual describes all the functions, and this is also the same as our documentation. For example, if you write in our question mark daily response, you will get information about daily response. So which arguments are needed, what is the output, and very short description. Here on the CRAN site, you also have two vignettes. So vignettes are so-called tutorials. And if you click on those vignettes, you will get a few examples, basic examples, how to use dendrotools, and yes, what you can expect. So there are two different vignettes. One is compare different regression methods, which is topic which won't be really covered today. So we will focus on the examples with daily climate data. So this is the, let's say the content of the dendrotools R package. Everything what I have shaded are just datasets. So I have included a lot of datasets to make examples running. So today we are going to use a Suite 272 dataset, which is from International Tree-ring Data Bank. There are also temperatures for Ljubljana, monthly and daily, but we will focus and explain functions like daily response Z-score, data transform, glimpse daily data, monthly response Z-score. So those functions which you can see here, years to row names, critical R, are just help functions for other functions. But because I believe they are also useful for you, you can check them out and maybe apply on your daily, on some of your analysis, if this will be exactly what you need to do in R. So, but we will not focus on those help functions today. So I hope you have installed the dendrotools R package. So this is a very usual, command, install.packages and then the name of the package. Alternatively, you can always install dendrotools from GitHub, as I said. So, but in the GitHub, the version is always under under construction, so it's not checked. And it's possible that if you are going to use the version on the GitHub, that you would run in some error. So I always recommend using the version from the CRAN, which is checked and tested and will definitely work as you expected. But for example, a few days ago, I got an email from a researcher asking me to add one feature into the dendrotools, and because it usually takes 3 to 4 days to publish package on CRAN, I have sent him this version, and he was able to use this additional feature in in 4 to 5 hours after he asked me. So this is useful for quick communication between the community. Okay, there are a few papers. I have mentioned those in my email. In 2018, the dendrotools was first time introduced in Dendrochronologia. And then in 2020, last year, I again presented new features in the dendrotools, which will also be checked and tested today. So the bootstrap, partial correlation coefficients, and all the functions which exist for daily data were also, let's say, downgraded to be used also on monthly data. So this monthly, let's say, monthly functions were added with one purpose, and this is that I was able to compare daily and monthly approach. And this was published in this paper in Quaternary Science Reviews with the goal to show the community what is the benefit of applying daily functions instead of monthly. So you're very welcome to see some of the findings in this paper. Okay, so now we are going to study and focus the main function of the dendrotools R package, the daily response function. Okay, so If you check the manual of the daily response, so you will get something like that. So short description, and then here is the list of all the arguments. So what are the arguments? So daily response is a function which takes arguments. So arguments is what you need to provide the function that it's going to work as expected. So usually arguments have some default selection. For example, default method for daily response is LM. Then default metric is R squared. So if you don't change those, they will be used as default. But as we will do it today, it always makes sense to change the default values so you can adjust the analysis based on your research. So there are many arguments, as you can see, but only a few of those the arguments are really important. So I have marked those are important arguments in bold. So response, then climate or environmental data, method, and correlation method, and the limits, which I'm going to explain in the next few slides. Also the previous year, and of course remove insignificant and alpha and row name subsets. So those maybe 7-8 arguments which I have now listed will be explained in detail in the next slides. To other arguments which we are going to address later, because I think first we should get the main idea, then we should do some exercises, and only afterwards we'll try to get some details and to see how we can further adjust the function to serve us. Okay, so regarding dendrotools and the daily response function, I received many questions from the research community, and I would say that 80% of all questions go to how to properly prepare the data. So I think that this is a very important aspect of this webinar, so please pay attention. So to analyze the daily correlations between climate data and your chronology, you need two data frames. So in our data frames are actually tables or also data tables, but I will today use the expression data frames. So in the first data frame, you need your chronology. So tree ring with index, okay? This is exactly the same format, or let's say almost exactly the same format as in the dplyr package. So dplyr package from Andiban is probably the most used in dendrochronological community. And with this package, you usually you can standardize your data and build chronologies like this one. So in this webinar, we are not covering the basic dendroclimatological principles like sampling, standardization, and chronology building. So I hope that all of you know how to get from trees in the forest to chronology like we have here. Okay, and then the next data frame which we need is so-called env_data. So I have decided to keep environmental suffix instead of climate, just because it's also possible to use non-climatic data, like some pollution data, which is based on daily observations, would also be possible. Or I don't know, I don't have any other idea, but I'm sure that there are other environmental effects which could be compared with our tree ring chronology or tree ring index, for example. So you need data frame with 366 columns, and n number, of course, this n refers to the number of available years, which are always inserted as row names, like here. So in the response data frame, we have one column And then we have years, which are indicated as row names. I will show you later how we can do this. And this is exactly the same in the environmental data, where we have 366 columns, variables. And the first column represents January 1st. Then we have January 2nd, and so on. And the last is December 31st. And again, we have years inserted as row names. Okay, and in the next few slides, I'm going to explain you what is the idea behind the algorithm that is used to calculate correlations between aggregated daily data and our response or tree chronology. Okay, so a few more arguments which we will now mention is the aggregate function. So the aggregate function, you can use mean, median, or sum, is used to aggregate the current selection. So we have, for example, as you will see, we work with the so-called moving window, which is moving through the data, and it changes its size, and each step we calculate, for example, correlation coefficient. So when we start, we have to decide about two very important arguments, so-called lower limit and upper limit. So lower limit is the, let's say, the narrowest sequence of days which you are ready to consider, because we can also start correlating individual days. For example, I would like to correlate January 1st with my tree chronology, but I hope that we all agree that this doesn't make any sense, okay? Because then I would say, yes, this specific day is affecting my chronology, but this is not true. So what we are doing here is we are aggregating, so a higher number of days. So what is this reasonable minimum? I don't know. So I usually use 3 weeks, because I think that when we work with high elevation sites, this window, well, let's say the minimum window could be relatively narrow, but for sure it cannot be just a few days. So it has to be maybe 2 weeks, 3 weeks, month, or maybe, So usually, as you will see in the results, this optimal window is then maybe 1 month, 30 days, 2 months. But for the sake of the analysis, you have to decide what is the lower limit. We will now use this lower limit as 4, okay, just for the sake of demonstration. But don't use lower limit 4, apply it as higher, maybe 2 weeks or 3 weeks. And then the upper limit, this is the maximum series of days which you still believe is reasonable to affect your tree chronology. So this maximum, I usually use 9 months. You can also apply as 12 months. So usually I allow this to be relatively high, just to allow the exploration of different responses. Okay, as I said, just for the sake of presentation, because I would like that you see what is happening behind, let's now use this window width of 4. Okay, and in the first step of the algorithm, the function is going to start on January 1st, and it will consider next 4 days, okay, because this is a window width of 4. So from January 1st till January 4th. And it's going to use the method. So first it's going to aggregate this data. So using mean, median, or sum. So in this case, I have temperature. So I would probably apply mean, calculate mean value, and then in the next step, compare this value with my chronology and save the calculated correlation in the final output matrix. Okay. Next, okay, in the next step, the window goes +1. So we are now January 2nd, January 5th. We are aggregating these days to get mean temperature for each day. And in the next step, again, correlating it with our chronology and saving in the final output matrix, and so on. Then January 3rd, January 6th. So as you can see, this window is sliding plus 1 day, and at each step it's calculating correlation between aggregated data and our response reading width, so standardized reading width. Okay, so this is now going and sliding, and when this window reaches the end of the year, so December 31st, it starts from the beginning. Okay, but in this case, we have now window width of 5. So at each step, it goes back to January 1st, but it increases for 1 day. And now we are using, so we are considering January 1st, January 5th, aggregating temperatures to obtain, to get the means, and again comparing with our response and getting the correlation saved, and so on. Very important information. So as you can see in the final output matrix, we have also so-called row names, and this index at the beginning of the row indicates the window size which was used for the calculation. Okay, so we have here 4, we have here 5, and you can imagine that in the next round we are getting to 6. Okay, and next very important information is that the position of correlation within a matrix exactly defines the position of this window. Okay, so if this correlation is saved on the first place, which means that it started on the 1st January. This correlation started on 2nd January and lasted for 5 days. Okay, so very important to note that, because many people then use this the final output matrix, and they try to do some conclusions based on it. To understand where is the position of this particular correlation, you have to consider the position and the index at the beginning. Okay. So yes, now we have a window width of 6, and this is so this is the idea. This algorithm would now continue and make very big matrix of all possible correlations between consecutive days. Okay, and what we get at the end is something like that. So if you have very good eyes, then you maybe see something, but just in case, let's increase it. Okay, so this is now an example of more realistic analysis where we started with 21 days. So in this correlation, for example, yes, started, was calculated using data started on January 1st and then till January 22nd. Okay, so it's important. You always have to use so January 1st plus 21 days minus 1, because both days at the beginning, at the end are counted. So this is important. Yes. So this is now the main output of daily response. You get all the calculated correlations, and because we know how we calculated those, we also know where is the, for example, highest correlation present. Okay, what to do with this now? So the first option is to plot this matrix. We will use automatic plotting functions in R later, but all these correlations, if we plot them, we get so-called heat map. So heat map shows how some value changes based on its location in the matrix. And this is a very common presentation of this matrix. We can see, for example, in this case, we have the highest correlations at the beginning of the year, okay? And then we also get some negative correlations at, here around the day of the year, 100. So we usually work with this day of year, and you have to approximately know when is summer, when is July, but later you can also customize and maybe change this plot. So day 50 is somewhere at the end of February, then day 100 is somewhere at the end of April, and so on. So you can see that there is a lot of values. I have written here that if you consider lower limit 21 and upper limit 270, you will get 55, yeah, so slightly more than 55,000 of calculations. So like in this case, why is here blank? So I hope you all understand why this is blank area. This is because at each year, so at each step, we increase our window +1, which means that we have one correlation less than in previous case. Okay, so in this case, this is the 2021. So in this, so when we are increasing this window, so for example here, this is a window width of 250, which means that the first correlation was calculated using the aggregated daily data from January 1st till day of year 250, which is, yes, already somewhere in the summer. Okay, so just that you know why it's this blank area on the upper right side of the heat map. Okay, so we have explained the response. So those are the key arguments of the daily response. Response, this is your standardized reading with chronology. Of course, it can be anything. It can be also chronology related to so isotope ratios, to wood anatomical parameters. So blue intensity, maximum late wood density. So any proxy which can be derived from 3 rings. So it's not just ring with chronology. I hope this is clear. Then we have environmental data in terms of climate data. And then the method. So method, we will explore this later, but usually I use correlations. You can also use linear models, which is equivalent, but just you will get squared correlations in terms of explained variance. And we can also use non-linear models, non-linear. So at each step, we would not be calculating correlation coefficient, but we would be fitting non-linear model and extracting explained variance between the aggregated daily data and our response. We will do this later. The aggregate function, as I said, mean, median, or sum. So I suggest you always use mean for temperatures and sum for precipitation, but the selection will not affect the correlation because the variance stays the same. It doesn't matter when you are summarizing your data or making the average. So you will always get the same correlations, but for the interpretation purpose, I think it's really important. Later you will see when you are extracting the calculated aggregate data, it makes much more sense if you have applied sum for precipitation data and mean for temperature. With the lower and upper limit, we define this window of research. So we start with a reasonable low number, not too low. If you will start with less than 14, dendro daily response will work, but you will get a warning that please think about what you are doing, because you can also get some so-called spurious correlations. And the upper limit, I suggest to set it reasonably high, just to see that when you are increasing the window, the correlations should somehow be reduced, because the optimal window usually lies just between 1 and 2 or 3 months. So usually it's not brighter, but it could also happen. Okay, now let's see some of the additional arguments. So correlation method. So this is the argument with which you select whether you would like to use parametric method. This is person, and this is the default. But in some cases, I know that people like to use non-parametric method for correlation calculation, which is Sperman or Kendall. So decide for yourself. This is an option. Then one of the very important arguments which you must know is so-called row names subset. It's usually the case when you work with the dendroclimatological data that your response, so your chronology and your downloaded data will not exactly overlap. So this would be a very rare and unique case. Therefore, if you properly prepare the data, putting years in the row names, then you can simply use row name subset, which will compare row names of two data frames, find the overlap, and for the analysis, it will use, like in this case, only 2013 till 1996, but this is only the demonstration. So if you apply row name subset, you don't need to subset your data prior to the analysis, but you're free to do so if you would like to do it. So row name subset is by default false, because I want that users understand those important arguments, and as we will do it later with the exercises, so always set it as true. Next, the effect of previous year. So in dendroclimatological studies, again, we often observe that what happened in the previous year, maybe at the end of previous growing season, has the effect on our current on our current tree-ring chronology. That's why if you apply previous year equals true, the analysis will also consider what is the effect of climate from previous growing season, and you will get much bigger heat map. So you also get correlations calculated from the previous year. Of course, this takes much longer. It takes longer, and then when you interpret this, you need to again understand that there are 366 days from the previous year, and 367th day is then the first day of the current growing season. So we will do analysis using previous year as well.
Sorry, Erne, you have one question.
Yes. Okay.
Question and answers.
Let me see. Okay. Okay, Hanekar. So from lower limit to upper limit, dendrotools uses steps of 1, as daily response might take some time to run. Is there a possibility to set the step to equal 10 in order to reduce runtime? Well, no, thanks for idea. Actually, for now, this is not an option. But I agree with you that this would actually make a lot of sense to include, especially when we are using the bootstrap. So even if you use a very huge number of possible windows, you will get the results in less than 1 minute, or if you have a slightly faster computer, in 30 seconds. But when we are using bootstrap, this might take for 6-7 hours. So usually if you extend the analysis for the bootstrap, it takes longer. And especially if you have, for example, yes, maybe hundreds of chronologies which you would like to run through the analysis using the bootstrap, this would make a lot of sense. So thank you very much. I will definitely consider this to implement in the future. I think it would make sense. I have to write this down. Okay, so yes, so I have now explained what is the previous dot year for, and now the last two arguments which I would like to mention is remove insignificant. Okay, if I go one slide back. Yes, okay, so usually if we plot all the correlations, we get something like that. So this is the heat map. So if you have very good eyes for colors, you will be able to see a lot of information out of it. But if you're like me, also having a little bit of problems with the colors, then I suggest you simply apply the remove insignificant equals true and the alpha argument, which is by default 0.05. But using these two arguments, it will remove all insignificant calculations. And you will remain and you will be able to observe and to report only the significant effect of significant correlations between chronology and daily data. So I think this is a very nice feature. And but very important is if you set this alpha argument too low, so for example 0.001, and you have not so sensitive chronology, it is very likely that you will not get significant results, and in this case you will get error. So if you use the remove insignificant equals true, make sure that you set the alpha so high enough to get at least a few significant correlations. So this is, I mentioned before, most common problems or questions which are related to the preparation of daily data. Second, the most common problem is when people use and get all non-significant correlations, and then I just recommend them. So use remove insignificant equals false, or even better, use maybe not 0.05, but use alpha as 0.1, for example. So you can still remove very low correlations and get some significant, but less significant than 0.05. Okay, and the boot. So boot was recently introduced. And if you apply boot, so boot equals true, then you have to expect that the example and then the daily response will work for, yes, at least 1 hour. Of course, it depends on your settings. But this is, for example, if you set a lower limit equals 21 and upper limit equals 270, this is going to take approximately 5 to 6 hours. So this is quite a lot. And again, thanks for the suggestion regarding this, not so fine step, but lower step, which would then enable faster analysis in these bootstrap cases. But in this case, if you use boot equals true at each step, so if I will now go back just to demonstrate this, I think it's important. Okay, so now at each step, we are aggregating this temperature data and calculating simple correlation between tree with index and our aggregated series. But if you use bootstrap, now we are applying bootstrap on these two variables, and first extracting the mean correlation, which is going to be saved here, and second, we are going to save lower and upper limits. So we don't have only final output matrix, but we have final output matrix related to lower limits and the final output matrix related to upper limits. So each correlation which is calculated has also the so-called confidence intervals. So that's a very desirable feature in the research. So you can also report the uncertainty related to your calculated correlation. We will do examples related to Bootstrap in the next session. I think so. We are okay. We have clarified what is boot, and with the boot _n, you define the number of bootstrap samples for each step. So I suggest you use boot equals 1000 or higher. But again, the higher this number, the more time it takes to calculate all the bootstrap samples. I use it as 1000. Okay, so we have now finished the part 1. So this was the introduction, and I have explained the daily response function. We are now going to take a short break. Let's say approximately.
Before that, do you have time to answer one question, please?
Absolutely, absolutely, yes. Before we go to break.
Juliana Nogueira, she asked, when you get climatic data from reanalysis, for example, which data comes from in .nc. How do you recommend to organize the data to appear as we need?
Yeah. Okay. Yes, this is a netcdf file, like from the EOPS. So I have yes. So you have to know how to extract the data, and you have to convert it into a table. So you cannot directly use the NC file inside the dendrotools. Well, so if you send me an example, I can provide you the R code how to do this for one example, and then you can use it. No problem. It should not take me too long. But otherwise, if you would like to do this work by yourself, also of course do it. But if you need help, I can help you with the coding. So you just have to go inside the file, see the names of the variables, extract it, and then transpose it into the matrix of 366 days, and then put the year indicator in the row name. So if you need help, please let me know, and I will help you with that. Okay, great. I see it. Thanks. Okay, so if there are no other questions for now, we meet in, let's say 15 minutes, because we are very well scheduled, so we don't need to hurry. We meet in 15 minutes, and we are going to continue with examples in R. So that's all for now, and see you later. Thanks.
Yeah, you have one question on Q&A.
Okay, thanks. Okay, let me see. Yes, so the question is from Andrei Popa. Hello. Whether is it possible to limit the analysis period inside of the year, not to run from day one from previous year to last day, but just for example 120 to 630 in case of previous year is considered as well. Well, at the moment this is not possible, and there were some suggestions to do that. But in this case, if you would like just to limit, then I suggest you simply delete the calculated correlations afterwards, because you get outside the final output matrix, and afterwards you can simply say, I will ignore everything what was calculated at the beginning of previous year, and then I will just accept what is calculated between this. You have mentioned 120 and 630 days, which of course I understand why you have selected exactly those. But at the moment, this is not possible. And if I would start implementing this suggestion, I think this would probably completely change the strategy, how I calculate and how I save the calculated correlations. Or I could simply allow you to make the restriction and then delete myself the calculated correlation. So this would actually be possible. Actually, I will write this down just in case. So limit the considered windows. Yeah. So I understand, because you don't want to, for example, get the effect of January from previous year. So for now, let's say that you will have to delete what you are not interested in, and use only what you would like to use for maybe publication or something like that. Okay. So Okay. Okay, thanks. If there are no other questions, pardon, I suggest we go on with the exercises. I will again share screen. And so we go now to exercise number 1. And our first task is to properly prepare the daily data, let's say. Okay. Okay, Diogo, so let me know if you see my RStudio.
Yes, perfect.
Okay. So we will skip the first line because this is something I believe you have already done. So installing the dendrotools package. This is the RStudio. I believe that most of you are familiar with this, let's say, supporting software for R. So I can't work in R without the RStudio. I really need it. So let's quickly review it. So here you have down is console, and here is your script, which you can modify and then save. You can add another script using the new file, for example. Then your data, which is currently opened, you can see it here in the data tab. You can also see the history, connections, and in case you are working on R packages, you would here get GitHub icons, and also all the plots, which we will plot later, will appear here in the plots. You can also see the packages which you have. So I really like RStudio, and if you are beginner in R, I highly recommend you start learning using also the RStudio. Okay, so I will empty my environment. And now at first, we always, when we work with packages, we have to open and call the package which we need. So in this case, this is dendrotools R package. And then we are going to use data. I have mentioned this already at the beginning, Suite 272. So this is data downloaded from International Tree Data Bank. I have selected this actually more or less randomly. And please see the original source and publication related to this data. So let's, okay, I have to call this. Okay, if you would like to see what is inside the data, you can simply click on it, and it will appear as new tab on next to your R code. So you can see that this data is already prepared as it's supposed to be for the daily response. So we have our tree ring with chronology, which starts in 1739. And if we slide this until recent, so here it's 2011. So it's, yes, you can see. So for the dendrotools, it is not important whether the recent year is down or up. So it's the same. And the same is true for climate data. You can organize it as in the descending order or increasing order. Okay, we will also, okay, we can see head and tail of this subject. So now we have, Suite 272, this is subject, and we can see the head and tail using the head and tail functions. Just in case, I would like to show you some of the, let's say, very commonly applied functions in analysis of dendroclimatological data. And now we are going to use Suite 272 daily temperature. So I have downloaded this from the EOPS. This is the EOPS observations we have discussed at the beginning of the webinar. And again, just use the data function, and let's see what is here inside the EOPS. Okay, so we have two columns, two variables. The first one is date, and the second one is the average, so the average temperature for this side. And as you know, we need something else. Okay, I have designed a special function in dendrotools, which is called data transform. And if you have data with exactly these two columns, date and then some climate variables, you can use data transform and simply apply the only argument, or let's say there are two arguments. So switch to 72 daily temperatures is the input, and then you have to specify the date format. And in this case, we have year, month, and date. So you have to use this epsilon, m, and d as indicator of what date format we have. And then another argument is format, it's daily. So we would like to get daily data out of it. Okay, so because later we will also use exactly the same function to transform daily into monthly, but this is now not important. So if you just simply apply this function, what you get is data frame with 366 columns and in this case 70 observations. And as you can see, we have years indicated as row names. So those are the row names which I have mentioned today several times. So this function data transform, it's I believe very useful, especially because when you download data also from Climate Explorer, you will get it in very similar, usually in many cases also exactly the same format. So date and then the variable. But I don't want to make this too easy for you. That's why I have decided to also do this manually. I would like to now use what is inside the data transform function, and we will do this exactly the same step by step using the LibraryDate-R package. So why I'm doing this? Because it's very likely that you will get slightly different format. Maybe you will not get date, but maybe you will get two columns, or three columns, year, date, month, and you need to know the basic idea how to manipulate dates in R in order to prepare daily data for dendrotools. So LibraryDate is, in my opinion, the best package for working with dates in R. And I have sent you a script with required R packages, and I believe you have installed LibraryDate already. So again, we are now going to use the data because we will overwrite what we have already done. So again, if you see here, we have only two variables and a lot of observations. And now we would like to transform this back into data frame with 366 columns using the functions from the LibraryDate. Okay. So first, let's check what is the class of date. Okay. So class will indicate what is what is behind this variable. Variable could be numeric, it could be character, it could be factor. There are other types of classes, but also the type which we want now, it's date. Okay. So if we check the class of this date, it's called factor. But we need date so we can apply specific functions like extracting day of year, extracting year out of date. So we need to transform this date into date. Okay. So date into date makes sense, right? Okay. So the function which we need is, we have used this before, it's called epsilon md. So this is directly from LibraryDate, and we have to apply epsilon md because this is the order and the specification of our date function. Okay, so in case we would have day, month, year, we should also then change this into dm epsilon. Okay, and if we now apply epsilon md on this date variable, we are going to change this into date. So if we now check the class, so the class will return information what we are working with. We now see we are working with date. Okay, the next step is to extract year out of date. Okay, and to do that, we are going to use, you could guess, function called year. Okay, and we will apply this function on the date column. I hope this makes clear. So in R, if you would like to use specific variable or specific column, we use this $sign. Okay, so with the $sign, there are also other ways. You just simply call this date. If we can run this now, you can see we get all the dates. And now we are going to add new variable into this data. So daily temperatures, which the name is year. Okay, maybe it's a bit confusing because we have year here and year here, but this is just a coincidence. Okay, so if I run now this this function and see the head of daily temperatures, you will see that we have now three variables: date, then we have our average temperatures, and then the year. Okay, this is what we need because later we are going to transpose this and also see what is down. Yes, we have also here year, and the last date is July 31st in 2019. Okay, next what we need is to extract so-called year day or day of year again from date. And to do so, we are going to use function called year day or epsilon day. So let's do it and check the head. So now we have additional variable here. We have called this do epsilon, which usually indicates day of a year. And we see that January 1st is the first day. And then January 2nd is the second day, and so on. And December 31st is the 366th day. Okay. And also,
so
let's see.
You have one question in Q&A.
Yes, let me see. Does the data transform check for continuity, check for missing days? Yes, so it does. Yes, it does. So if you have missing value or missing date, you will have at the end missing value in the transform data. You can check this. For example, if I go now back, so you can see in this case that okay, I have to click keep answer live. So you can see that in this case, the last date is July. Yes, it's July 31st. If we go back to data transform and we transform this data, we will get the complete data frame, but the dates from July 31st are going to be missing. Okay, this will now not be shown because in the RStudio I cannot scroll there, but I will show you later in the plotting exercise that all the missing values will be also missing inside the transformed format. But if you have like completely missing row, the function will understand this, and it will again add missing value. So the data transform will generate a sequence of days, and then it will merge what is inside the data. And if you don't have a specific date inside your data, this will be a missing value. So you won't get wrong results. Okay, we have the okay done. Okay. So let's get back. So there is we have arrived to this. I will just run this. Okay, so we have added day of year, and now we have 4 columns: date, then the climate variable, year, and doi. Doi, it's like day of a year. Now we will delete the date because we don't need it anymore. We will simply apply the null, so like delete this specific variable. And now we have only three variables. And if you think about this, is exactly what we need. So now we need to transpose this. If you use Excel, I think there is a function called transpose, And yes, I see. Thanks. And using this transpose, we will just we will use DOI as column names and year as row names. And what is then the information inside the data gets from climate variable. And to do this, we need reshape2r package and the dcast function. So in the dcast, in the first argument, which is actually formula, just indicates how we would like to transform our data. So we have year versus DOI, and our value is saved in the average temperature. And if we now apply this dcast, we are getting exactly what we wanted. So now, as you can see, we have year versus day of year. Okay, and if we go, we can go just by the day of 49, but it goes by 366 days. One important information. So you see that at the moment we have 367 columns. Why? Because we have year as a variable and not as a row names. So we have to move this into row names, and that's why we will use row names. So it's a row names function, and we will now apply. So we will, let's say, insert in row names exactly the same variable. So let's see it now. So we have here years, and we have years also in row names. The last step is to delete this year to get exactly what we need. Okay, we now delete the year, and we get the table which we need for the dendrotools: 366 columns and 70 years, in this case 70 rows. So of course you can do this also in other with other software like Excel, but I really recommend that if you plan to use R in your career, that you understand and master some of those very straightforward and also very simple functions, because they will be very handy for your research. Imagine that you have that you are working, for example, with the National Turing Data Bank, which has thousands of chronologies. So, and if you would like to apply dendrotools on all chronologies, you cannot do data transformation inside Excel because it will take too much time for you. So highly recommend investing some time in studying R, those additional functions, because they will be very useful for your day-to-day analysis. Next, I would like to show you the function also from the dendrotools, glimpse daily data. Okay, this function was designed simply to show you and to plot your data. So you see that you have a reasonable range, that you have missing values on the right place, and as the now related to the previous question, all the missing values, like we did not have data from July 31st on, now they are marked as black. So this is you can change this color to anything you like. Maybe it could also be pink. So this is the only argument, and this is just for you. Before you're starting, you can check the data to see if it's reasonable. If it would be precipitation data, it would be slightly different. Maybe later we can also check this on precipitation data. But yes, this is it. So next, one of
you have one more question?
Yes, of course. How do you deal with non-leap years? Okay, I was expecting this question. Okay, so in non-leap years, like usual, we have here every fourth year is a leap year, which means that we have here we have only 300. So in the leap year we have February 29th. Okay, and it's completely up to you what you do with this day. You can see that normally we put this day at the end of the year. So this is then 366th day. And in non-leap years, we have only 365 days. So you could also so the missing values which are here at the end could alternatively also be missing here. So February 29th, let's say it's somewhere here. So it could also be blank here. This will not affect your results by any means. Maybe, you know, in 1 in a million, it will have some effect, but very likely not, because we are in any case aggregating our data. So if you would like to have February 29th missing year for non-leap years, then you would have to prepare data in Excel and specifically force this and organize it in this direction. Because in the data transform function, we are using this day of year. So we are extracting, and in non-leap years, we have 365 days, and in leap years, we have 366 days. So that's why we are just getting missing value at the end, because we are just at the end stacking each year by each year. How do you complete those missing values? Oh, yeah. So, well, again, so you could, yeah, if you think this is important, while I think for the analysis it's really irrelevant, you could simply, yeah, you can maybe say that day 366 for non-leap years is the same value as 365. So you just duplicate the last 2 days. This would be one option. But because when aggregating, dendrotools daily response will actually use na.rm, which means that it will skip the missing days. But in this case, if you would like to generate additional date, then you would actually give higher weight on this specific date. So I don't think it makes sense to anyhow change this this format. But if you would like to, you have to do it in Excel or manually in R. So that we don't have the data for the entire year. Oh, okay. So if you don't have the data for the entire year 1990, yes, again, so there are two options. You could, yes, you could simply delete this year and delete it also from tree rings. This is one option, but then you cannot apply previous year analysis. You can delete year in climate data, and you can also delete it in tree rings. This would not, so this would mean that, yeah, you are still analyzing the effect of climate on tree rings. This is one option. The second option would be that you, yeah, try to interpolate the data using some of existing, software, or maybe try to find another. If you find data which is similar to your, and then using some linear models or non-linear models to impute missing dates. This would be the only option I see. But if you have a lot of missing days, like in this case, I have half year of missing values, I will never use this. I will skip this year for sure. Yeah. So I hope I answered your question. If not, please type in the chat or in the Q&A. Yeah, I always forget to click answer. Okay. Okay, let's go on. So yes, next feature which I would like to mention is how to modify plots from dendrotools. So all the plots which are returned from the daily response or glimpse daily data or other functions are so-called ggplots. So ggplot2 is probably one of the most popular and most common plotting. Yeah, so let's say plotting options of in R. So which means that you can, by knowing the ggplot2 syntax, you can very easily customize all the plots which are returned from the dendrotools. For example, let's now open the library of ggplot2. We will now plot this specific daily temperatures and add a few lines of additional code. So we would like to remove the legend, and we would also like to change the gradient of this specific output. So let's just apply it, and you can see that we have now completely different plot just by adding the plus sign and some fun. So to do this, you need to know ggplot2. It's very easy to learn. I would say that within 1 week you can master this. Then it takes some time to practice, but it's really desirable and in my opinion far the best for plotting purposes for scientific publications in R. Okay, and then you can also save this using the gg save simply, and if we now go to we have now saved this in the folder in the current working directory. Okay, it's here now, so I will now delete move this. Okay, now it's time to run the first so-called basic example for daily response. We are going to use.
You have one comment on the chat.
Okay, let me see. Glimpse daily
Just
data.
about our color scheme, yeah.
Okay, just let me see more logical colors. Yeah, absolutely. I agree. So the color scheme here is just random. I agree. This would be more logical. Okay, so let's now run. Finally, let's now run the daily response for the first time. We are going to use suite 272 chronology from response and suite 272 daily temperatures, which we have prepared. So for environmental or climate data, always use row name subset, because if I delete this now or comment out, this will not work. We get error and we get very informative instruction. Length of environmental data and response records differ. Okay, the argument, the function recognized as that the arguments have different number of years, and it won't work. So you can manually subset, or definitely more easy, use the row name subset equals true. So just for those who doesn't know, if you use the hashtag, this means comment, and in this case, this is the same as if I delete this line out of the script. And we will use method equals score, so simple correlations using the person method. Okay, so I have to delete the hashtag. Okay, now as you can see, so we are using the default lower and upper limits, which is default for lower is 30 and default for upper is 90. So this is a little bit more restricted analysis, but just just in case that we will know what is the output going to be. Yeah, so while this is being calculated, you get here the information about the progress bar, and when it gets to 100, we are done. Okay, class basic example. We discussed before different classes, numeric, character, date, and now we would like to see what is the class of basic example. So this is DMRS. So this is daily monthly response, just for you to make some sense out of this. And this means that now I can apply some specific generic functions in R, which were of course written by me for this specific class, but it will provide some reasonable output using the summary and plot and other functions which are so-called summary, so-called generic functions, S3 generic functions. Okay, so if you apply summary on basic example, you now get some of the first insight into this analysis. So you get information that we are doing daily approach. We are using correlation coefficients with the person method. So metric, in this case, we get NA because we did not use linear regression or nonlinear regression. And in this case, metric would indicate R squared or adjusted R squared. Then we get the information about the analyzed years. In this case, this is 1950, 2011. Also, the maximal calculated correlation, this is 0.41. Lower and upper confidence intervals are empty for now because we did not apply the bootstrap. And at last, you get the information about the optimal climate signal. So the optimal climate signal it's maybe the best way indicated here, June 18, August 16. The length of this optimal window is 60. We did not analyze previous year, and so June 18, this is day of year 169. Okay, so this is the first output of the function for you to get the some of the results, some of the descriptions about the methods, and most importantly, I always highlight the highest calculated correlation. Of course, I understand that correlations might be negative and positive. So in this case, I highlight the absolute value, okay? So you would always get information whether this would be negative, but if you get negative, which is higher than in absolute terms than positive, you would get here, for example, 0.41. Okay, now the next generic function which can be applied on this basic example is plot. Okay, so plot, we have two types, plot 1 and plot 2. So plot 1 is going to indicate, again, is actually a line plot which is indicating is the highest calculated correlation. So in the title of this plot, you get, again, the information about the analyze period method, the highest calculated correlation, and this window which returned the highest calculated correlation. And what you can see here is how this value, correlation coefficient, changes if we go slightly left or right. And in case we have only monthly data, we would be somewhere here, and this correlation would be approximately 0.35, I guess. So this is the first indicator why it's important or why is it beneficial to use daily data, because you can get those really high peaks like in this case. Okay, we will get back to this afterwards. So now I would like to show you the plot type 2. This is the heat map, and I believe that most of you, when using the dendrotools, would like to see something like this. So to see the climate effect on your tree-ring the effect of climate on your tree-ring chronology using so in this temporal pattern, let's say. What we see here is that we have the highest correlations. Yes, in this let's say part of the time. So this is summer, and we have a very high peak around day of year 170. And of course, if we go for one day left or right, these correlations don't drop so significantly. But if we go maybe 2 weeks left or right, this is significant reduction in correlation. Also, we get the effect of, we can see that there is also a negative effect, which happened at the end of the growing season, which means that if, for example, we have cold September, then this reduces the tree ring width. Very simple and possible explanation for now. Okay, so now again, I would like to show you some ggplot code which can be used for you to modify this legend, okay? Because this legend always differs. If you apply it on a slightly different data set, it may be just it may give you just positive values, or maybe if there are more negative correlations, this would be totally different. So just in case when you have more data, it makes sense to unify this color scale for all for all sites, for all examples. And to do so, I am providing here the scale fill gradient 2 code, and we are going to use the default, so which means blue for positive values and red for negative values. We have specified breaks, and we have also specified some limits. So if we apply this code, we get, in my opinion, much better much better plot. We have from -5 till +5. You can also maybe if you would like to modify this, for example, you can change this to -1 to +1, and you get different different scales. So we can also add breaks. So this is very important when you are working with different data with different sites and you would like to compare different sites. It's very important that you have unified scale and legend for all of your plots. So I think this is this is important.
Jarne, you have one comment in Q&A.
Okay. This code of modification is not available in the download. Yes, exactly. This is not available because I have added this only yesterday. So at the end of this workshop, I will again send you the link for the of the Dropbox, and there are a few changes which were added yesterday. So you will have the most recent version of the exercises. Thank you for notifying this. Okay. So, okay. Now, let's talk a little bit more about this basic example and what this actually is. Okay. So, when you apply the dendrotools, you have to save the results to one object, which you can name however you want. In this case, I have decided for basic example. So, in basic example, there is a lot of information which you can use for your research. And basic example is actually a list. So list is like a closet. It has, let's say different doors, and in each door there is something else. And if you want to take this out of this closet, you have to know the name of these doors. Like in this case, calculations, boot lower, boot upper, method, metric, and so on. So if you apply and give the name of this list, and then $sign and the name of this door, then you get what is inside the door. So lists are very special objects in R, because you can save inside, you can save whatever you want. Okay, because in tables you cannot save, for example, figures inside the table, but you can save figure inside a closet, so inside the list. So this is very important, and usually when we want to save something from the function, we save it in a list. Okay, so why I'm explaining this now? Because if you would like to get this matrix of, so final output matrix of all calculations, you have to apply basic example and then the calculations. I will now save this into the object called CALC, just because of better representation. And now this is our matrix. So you can see there are a lot of NAs because those are insignificant correlations and are removed. But if we scroll, till summer, we would get to this part of the image. So positive and significant correlations. So because many people then would like to do something with this matrix, maybe, not extract only the highest correlation, but also the second highest correlation, or maybe would like to analyze the difference between the highest and the lowest, or maybe standard deviation, whatever. So if you would like to do this, you have to extract and use this calculations which is obtained using the $sign and then the name. Similarly, if you are using the bootstrap, you have exactly the same matrices, but with not the mean calculated correlation, but with lower and upper limits. Okay, so in this case, we have boot lower and boot upper. Let's see this example. Again, we have here just non-significant correlations, but yeah, maybe not the best example, but this would be lower limit of correlations calculated on using the window from January 1st till January 30, so 30 consecutive days. The same is true for upper. So if you use the upper boot upper matrix, or yeah, it's matrix, then you can analyze the upper limits of all significant correlation coefficients. Well, okay, so what else do we have in this output list? We have information about the method. We used correlation. We have the information about the metric. Okay, in this case, you get the indication about the person. So this was the method for the correlation analysis. Analyze period, and then we have basic example type, so daily, and reference window. We are going to explain this in the next slides because this is very important to understand. Okay, and then we have so-called optimize return. I would like to explain this a little bit more in detail. So optimize return is, again, data frame with two columns. In the first column, you have your chronology, and in the second column, strange name, optimize return. But what is this? So this is the aggregated data using which was used to calculate the highest correlation value. If I now calculate the correlation between these two, I would get 0.41. This is the highest value. So this is the aggregated temperatures from, I think, June 18, August 16. And this is now what you can use to work maybe to. So this was designed for climate reconstruction models. Because if I now want to reconstruct climate, all I need is just this optimized return. And we will do examples, very simple examples, just for demonstration in the next exercise session. So this optimized return gives you the information about this, about the climate in the optimal climate window. Okay, then next one is so-called optimized return all. Okay, so this is exactly the same, but you have just one variable, and it is available for the complete. So for the complete period of available of the availability of your data. If you can recall, we had our analysis finished in 2011, but in this optimized return all, you get this aggregated data also for the years which were not included in the analysis. I see raised hand. Okay, so I will, if you want, you can write, or you are now allowed to talk if you would like to ask a question. Hussein. Okay, so if you, I see, maybe later, but if you would like to, you can simply ask a question, or in the chat you can write the question, or in the question and answers. Okay. So yes, we have. I have now explained what is the transfer function, optimize return all, and now the transfer function. So the transfer function is a scatter plot with linear indicator between our pre-ring chronology and our, again, aggregated temperature data from the optimal time window. So yes, if I extend this now, this is average temperature from June 18, August 16, and this is the scatter plot between between these two variables. This is our chronology. Okay, so temporal stability. Temporal stability cross-validation and the reference window will be explained in detail in the next slides. So I will now only show you what they are. But so in dendroclimatology, we usually would like to see if the correlations are actually stable in time. Okay, and there are different options for temporal stability. In this case, we have used the default values, which only splits our data into two parts. For example, 90-50, 90-80, it calculates the correlation coefficient. For what? For this, the highest, this optimal climate window. And now we do the same for, let's say, late period, 1981, 2011, and again, we get the correlation value. So we can see that the correlations, there is a difference in the later part. So in the later years, we have a higher correlation value, while in the early part, a little bit lower, but still, let's say, it's relatively stable. It stays significant at least. And the final output, which we're going to discuss, is the cross-validation. So what is the cross-validation? Again, this will be explained more detail in the next slides, but cross-validation is something that usually I again like to do to get the information about how this relationship between extracted climate and our chronology is stable in time. And this is usually done before climate reconstruction. So we split our data into two periods, let's say early and late, and then we have calibration, and we use the calibration period to fit model, and the validation, or maybe more often said verification, to calibrate, to evaluate our model. So there are a few statistics which are commonly used in dendroclimatology, like reduction of error and coefficient of efficiency. Recently, there was a new metric called the trended efficiency from Samuli Helama, but please see details about those metrics in the publications which I have sent you. So we can see that this data...
have one question on Q&A.
Q&A. Yes, hi Katalin. Is there a possibility to make this analysis using the rescale method instead of linear or non-linear methods, or a nested approach? If you are talking about the temporal stability or cross-validation, actually, no, I think no, you cannot use, of course, you cannot use the nested approach. So all you can do here, if you would like to apply some kind of your own methods or other methods which are not available here, so you can use this basic example optimize return, like here, and then you have here, for each year, you have ring width index, and then the extracted optimized return. So all what I have shown now, the temporal stability and the cross-validation, are done only using this data table. So if you would like to test this stability somehow differently, then you can extract this and apply a different approach. But that's all I can say for now. But if you have some specific suggestions, you can write me, and yes, we can definitely discuss if you have some suggestions for the improvement inside the dendrotools. Thanks. Thank you. Okay. So yes, we are now almost done with this first example, cross-validation. Yes, as I have said, you are getting you get information about reduction of error, coefficient of efficiency. In this case, they are not really reliable, especially because they are negative. They should be at least positive, but yeah, if possible, being not just positive, but also higher than 0.2, 0.3. So then you can really reliably reconstruct climate. But this is just demonstration. So to see what is the output of the function. Excellent. So this was the longest exercise. All next exercises will go faster. But now I promised I will explain a few details regarding reference window and regarding the temporal stability checks and cross-validation type. So, okay. So I believe you now see my presentation, Yoga?
Yes, perfect.
Yes, thanks. Okay, so the first concept which I would like to explain now is the different reference windows. So the default in the dendrotools, and which actually I use all the time, is so-called reference window equals start. What this means is that when calculating different correlations, the position of this correlation coefficient in the final output matrix is the same as the position of the window. So the beginning of the window. Okay, so in this case, our window starts on January 1st. That's why we are using here also the first position. Okay, alternative option is end. So if you use the reference window equals end, then the position of saved correlation will not be the beginning of this window, current window, but it will be the end of current window. So you will get slightly different output matrix. Okay, and the third option is middle. So the position is, you can guess, in the middle of this window. So we have here the middle is number 3. So, and this is also saved in number 3. So when we have, for example, 7 days, this is always rounded up, and then so that you understand that when there is no, I forgot the English name, divisible by 2, then it is rounded up. But when this is analyzed for the algorithms for the summary function and for the plotting functions, this is considered. So you will always get correct information from the dendrotools. So why is this important? So this is actually, this was the idea from a dendrotools user who didn't like this empty space at the end, and said, let's just have empty space at the both sides. Okay, so if you are using the reference window is equals middle, then the plotted correlations will have slightly different shape, but information is always the same. So in this case, we have it like a pyramid. So in each let's say window step, we have one correlation less, and this is then gets the visual effect of pyramid. In this case, at the beginning, we have seen before in examples, we get empty space at the end, because at each step we have one correlation less. And in the last case, if reference window equals end, so we are getting this empty space at the beginning, because we are always starting. So for example, this is a window size or window width of 90, and the position of this first calculated correlation is on the 9th place. Okay, so but as I said, this is the same example calculated using different reference windows. You will always get the same result. So the optimal selection is in this case is March 14, May 12, March 14, May 12, March 14, May 12. In all cases, you get the highest correlation coefficient calculated. It's the same. Only the plotting of these values is slightly different. So here you get the indication of day 132. So this is the end day. So you say the ending day of optimal window is day 132. Then you get the middle day of optimal window, day 103. And in this case, as we did in exercises, this is the starting day or beginning day. It's day 73. So this data is related to mean vessel area, which is mostly related to conditions in at the beginning of growing season. Next, we would like to see different options for temporal stability. So we have 3 different options for temporal stability: sequential, progressive, and running window. So if you use temporal stability equals sequential, then this is probably the most restrictive and rigorous test. Your data is split into k parts, like in this case, which are not overlapping. And for each part, you are getting calculated correlation coefficient using, of course, this optimal time window and your chronology. So in this case, we can see that we have a huge drop, also getting non-significant correlations for this, I think 14 years from 69 till 1983. But this is up to you. I'm just showing you different ways of testing the stability. Then progressive window, I would say this is the least restrictive. So we start. So of course, this K is used to control the number of splits. If you would like to have more splits, it will be even more rigorous. Use it K equals maybe 10. But if you would like to have less rigorous, use K equals 2, for example. Okay, then progressive window will again split your data into 5 different parts. It will start with 90, 40, 90, 54 in this case, and then it will just add additional years. So as I said, this is less restrictive. We also now don't observe this drop in correlations for this period, because this period is now including previous years. So this is just one option. And again, you control the number of splits using the K argument. And finally, you can apply the temporal stability equals running window. Actually, this is I like the most. And in this case, you have a different argument. It's not K, but it's K running window. And K running window, usually we select maybe 25 or 30, and it starts at the beginning using 30 years, and then progressing just +1. Then we have 41, 90, 70, 42, 71, and we can see how this correlation actually changes in time. And again, we do, because our window is now too large, or it includes years with highly significant correlations, we do not observe almost any drop in correlations in this case. So it's less restrictive, but it's up to you to decide which one to use. Okay, so the final information before we take another break is daily response and so-called k-fold cross-validation. So this is the consequence of me working also with the machine learning, where k-fold cross-validation is a very common term, and all the models which are used in machine learning are evaluated using so-called k-fold cross-validation. But actually, this is also what we often do in dendroclimatology, where we, for example, in dendroclimatology, we usually split our data into 2 parts, so-called early and late. And as I said before, we use the calibration data to fit model, and the verification or validation to test, to evaluate the model, and then you switch this and do it vice versa. Then the late part for the calibration and early part for the evaluation. But what I think it's also desirable and maybe should be considered more often in climate reconstruction models, to not use only 2 splits, but also more splits. So like 10 or 3 or 4, like it's usually done in machine learning. So in this case, I am showing you, if you use 10 splits, 10-fold cross-validation, your data is split into 10 parts. more or less equal. And then at each step, 90% of data is used for model fitting, and 1% of data, 10% of data is used for model testing. And this is then systematically done across all splits. And at each step, different evaluation matrices are calculated only for independent validation or verification data. And then we get information how our model performs on non-scene data. Okay.
Sorry,
so,
you have one question?
Yes, question and answers. Will it be possible to compute temporal stability for a specific window size, not only for optimal? Oh, so currently this is not possible. So if you would like to do this, you will have to extract data manually. But in the previous versions of the dendrotools, I had an option where, for example, users were able to define a specific period based on daily observations. And I think I will see if this is possible, because you could, before you start the analysis, you could say, I'm really interested in what is going on between, for example, July 15 and August 15. And then you would get this specific information. This would actually be very useful. And thank you for this question. I will write down your name, and yeah, I will think about it during the summer, try to implement this and come back with the feedback. Thank you. So add specific selection. Specific. I think this would actually extend the. So another question: is the date in each period? Is the date in each period in the temporal stability the same? So what do you mean by date? You mean, yeah. So if I go back to yeah. So the dates. So let's again see this and optimize return. Okay. So this is the data that is used for temporal stability. So we get here the years and then the optimized return, which represents this optimal climate signal. And then, you know, if you apply a running window, it just selects 30 years, and then it's calculating correlations and saving it in the another list, and then giving you the output. So if the temporal stability is sequential, then you get one correlation value for this period and one for this period. So cross-validation and temporal stability checks are done only on this data. But yeah, actually, you know the date, but you have to get it from the summary. Okay, so this date is always, yeah, June, it's June 18, August 16. Okay, so you get this information using the summary, or if you use, for example, plot number 1, yeah, you get exactly so, June 18, August 16. So you know this date, it's always the optimal selection. So the window which returned the highest correlation in absolute terms. But as Andre suggested before, I will try to implement also that you can specify one additional selection, and then you get, for example, temporal stability or any other tests of only for this selection which you would like to have. Yeah, I hope I answered your question. If not, please let me know, so I will add more.
Is it this date the optimal through time?
Yes, so this date is always the optimal, based on the optimal correlation. Yeah, yes, of course. So it's in the, yeah, good question. So it's, yes, it is the same. Yes, of course, it is the same. Like so, because also here, this date, this optimized return, it's always the same. This is always this is June 18, August 16 in this case. Okay, so we can go on. Okay, yeah, the last information which I wanted to give you before the next break is this cross validation. So when, for example, as I said, we can also use cross validation equal using different k numbers, like in this case, number equals k number equals 5, and then we also get different periods, so which are of course shorter in this case, but we get maybe more, again, more restrictive and more rigorous tests for our optimal selection. So I'm all the time talking about this optimal selection, which is based on this highest calculated correlation coefficient. Okay, so I see there are some questions, and I will, or this is already, yeah, okay, so this is, yes, okay, so we have answered all the questions and answers for now. What is in the chat? Okay, excellent. So we have now finished part 2. We have done some basic exercises, and we have also explained the temporal stability, reference window, and cross validation. Now we are again going to take a break. I see we are a little bit late, but I have, yeah. So I will go slowly through the webinar as planned. If I hope you have some extra time later, but also if you will have to sign out due to other obligations, the webinar will be available online later, so you will be able to get back and to see if you have missed anything. So thank you very much. Thank you very much for now. Let's take 15 minutes of break, and then we continue with exercise 2 and partial correlation coefficients. Thank you very much for now. See you in 15 minutes. Okay. Hello, everyone. I think we can now continue with the workshop, with the webinar, dendroTools. Now we are going to part 3. So we have one more thing to do. We have actually skipped exercise number 2, but it's quite short. So I will now go back to exercise 2, explain what is there, and then we can continue with the partial correlation coefficients. Okay, so. So Diogo, is everything okay? I see.
Yep. Yes.
Okay.
Go on.
Excellent. Okay, so the idea of exercise 2 is to test some additional features in the dendroTools R package, especially in the daily response function. So I would just like to show you some, so how the results change if you maybe apply previous year analysis, if you use boot equals true, and so on. So we are again going to use the suite 272 chronology. Now we are going to simply transform data using the data transform function. And in the first case, we will just slightly modify the arguments. We are going to use previous year equals true. Okay. So this might now take a little bit longer, but I think within 1 minute this is going to finish all the possible correlations which we have defined with the upper and lower limit selections. So always don't forget always to use the row name subset equals true. We're going to use method correlation, and we have assigned previous year as true. Okay, so let's see how is the summary. I have now saved the results, so the result list in T1. And if we apply the summary, what we can see here. So again, we are using the correlation coefficients, daily data. We don't get any metric information, and also lower and upper confidence intervals are different. But as you can see, now we have a higher correlation here. And why is that? So because we have considered also the effect of previous year, the highest calculated correlation actually is from the previous year. And this is the August 28, October 19. So this is the starting position of this window is day 240 of previous year. So now this is also a good example why it makes sense to consider the effect of previous year. Let's plot the line plot first. So now you can see we are getting so this is the row in a matrix which has the highest calculated correlation, and in this case this is 0.48, and this is exactly as we have seen this in the summary output, August 2028, October 19. What we were observing before, it's this peak, not exactly the same peak because the window size is not exactly the same. Before we had a window size of 60, now we have a window size or width of 53. But this is the positive effect of current summer. We can also see that in this case we are getting significant positive correlations resulting from the end of previous growing season. Okay, and also the heat map. So this is plot type equals 2, and again a similar story. So we are getting this very significant correlation coefficients here. Then also significant correlations with current summer, but again negative correlations with the end of current growing season. Okay, so actually this is very interesting situation where we have three distinct let's say periods, all temperature periods, which can explain our ring width chronology probably to quite a high extent. So this is this would also be possible to continue the analysis and maybe run some multiple regression models considering those different time of years and trying to explain the ring width index. Okay, so the next situation is to subset years.
Sorry, you have one question.
Okay, thanks. Hello, Jan. So is it? Yeah. So yeah. So Jan asked, is it possible to include the year before the previous year? Some publication shows that this can also have impact on tree growth. Well, this is again not possible, but actually not difficult to not so difficult to include this in the dendrotools. So I would say thank you for the suggestion, and I will do my best to include this as soon as possible. But I agree with you; it would make sense to include also the previous year and use it as for the analysis. Thank you. I will write this down. I see I will have a lot of homework after the webinar. Previous. Okay. So yes, in this next exercise, so T2, example test 2, we are now going to subset years. And this is one of the arguments which please pay attention. So you are able to subset your data and to analyze the effect of climate daily climate on your tree rings only for a subset of years. And this is especially interesting because if you would like to study how this optimal signal changes through time, all you need to do is just simply use the subset arguments, maybe in for loop, and you can then see how is this, what is the effect of time on this correlation pattern. So we will now use method and metric equals adjusted R squared. I will start running this. So when there is LM instead of correlation, you will get exactly the same result as correlation. So why I have included this LM? Because there is also a possibility in daily response to use multiple proxies. Okay, so you can theoretically prepare not only 3-ring with chronology, but also you can compare maybe early wood and late wood and analyze this in a regression terms. So in multiple regression terms, the effect of climate, or in this case, it would be vice versa. So the effect of different proxies on this current selection in time. So I have tested this several times, but I never find any good combination of proxies which would be first stable in time and non-correlated. So, but just that you know that this is also possible. And in the vignettes, which I have shown you before at the beginning of the dendrotools workshop, there are some examples, but the data is not optimal in this case. Okay, so let's see the summary of T2. You can see that now we have here linear regression. We are using adjusted explained variance, and in the final output matrix, what we are getting is not linear, is not correlation coefficients, but adjusted explained variance. Okay, so this is R squared and then adjusted for the degrees of freedom. Yeah, so as is usually done in statistic. Again, so we have now, I would say, very similar selection. We now are not using previous year, but we will focus on next exercises. We will focus on current year. And again, we get the optimal time window, June 19, August 10. So this is very similar as before, but since we are using a subset of years, 1980, 2010, of course, the result is not exactly the same, but still very close to what we obtained before. And yes, we can use plot type 1, so, and plot type 2. Okay, so next, as I said at the beginning, we will also apply nonlinear models. And the only nonlinear method which I which is currently available is so-called BRNN. So this is those are Bayesian regularized neural networks. And what is so, let's say, promising about this method is that it will usually fit sigmoid shaped function between 3-ring data and daily climate data. So as you can see, this takes.
You have one question in
one
Q&A.
question. Yes. Juliana, hello. I'm seeing that all graphs are related to a long-term mean, and the result would be related to period of the year with highest correlation with environmental data. But if I wanted to see the year in the X, I mean, I can input a site chronology, for example, and check across the timeline which year set the variable temperature. Okay, I have to read this once more. Yeah, long-term mean related. Yes, yes. Compute site. Okay. So, okay. So, Okay, so for example, correlation between a site chronology and NAO index. Well, I'm not sure. I have to say, I have never used NAO index. So is NAO index available on daily scale? It's only a year. Well, okay. Let's make a deal. Please write me an email with an example, and I will answer you in email, because at the moment I am not really sure about the question, and explain it a little bit more, because I don't have experience with this index you mentioned here, and I will do my best to suggest you how you could apply this with the dendrotools. Is that okay? Okay, so yes, thank you very much, and describe it in email, and if possible, provide some example data of this index, and I will do my best to assist you and help you. Thank you. Okay, so the nonlinear function is now executed, and first I would like that we see the transfer function. Okay, so this is the nonlinear function produced by the BRNN method. And yes, I agree with you. Is this linear or non-linear? It's very close to linear, but in fact, it is non-linear. And the difference between linear and non-linear, in this case, it's actually only for extreme values. So if I would now draw here a line, this would be something like that, right? And what you can see that, so non-linear function in this case would go in this direction. And when we would reconstruct climate using extremely narrow rings, this would affect this reconstructed temperature for narrow rings. While for linear, we would go in this direction. So the difference between linear and non-linear methods, which is one of the main output of my PhD, is important only for extreme values, and makes difference only for extreme values. Also in this side, if we have extreme wide rings, in this case, can I use this? No. Yeah, so if we have extreme wide rings, like with the index of 2, for example, non-linear estimate would be somewhere here, while linear estimate would be much up. So this is one of the greatest or most important differences between linear and non-linear methods. And if later we are going to compare climate reconstruction using both methods, you will see that the effect of selecting non-linear is only important for the extreme values. So let's also plot the, but again, we are getting the explained variance. So you can see that the values here are in terms, so those are not correlations. We have only positive values. Again, we have the highest climate signal, the highest correlations somewhere here in the middle of the summer. And we are now considering only a few windows. So I think from 50 till 67, 67, because otherwise this would take too long. So please explore this. And if you think this is okay for your research, I'm really a fan of nonlinear methods as well, but have a feeling that currently it's more easy to publish research in dendrochronology using linear methods than nonlinear. So, but I hope that the discussion regarding this will go on, because if we think about the response of trees on climate, and if we now discuss what is more possible in these extreme parts, I would vote that trees in this part will not respond linearly, but will possibly respond non-linearly, and also for the extreme upper parts. But maybe this is discussion for next summer, the workshop next year. Okay, now I'm going to just start running the bootstrap example, and we will leave it because it will take approximately 5 minutes. And in the meantime, we go back to slides to discuss the next topic, which is partial correlation coefficients. And then we will go back and also see the output of this last test number 4, so of the example 2. Okay, so now we start with the next function actually in the dendrotools, which is called daily response C-score. So why C-score and what is C-score? So C-score was first introduced, I think, by Dave Miko in 2011. He published and developed a software which is called C-score, and is available for MATLAB. Then in the dendroclimatic package, Christian Zhang also introduced a function which is called C-score and is available for monthly data. But C-score is designed to calculate partial correlation coefficients between your 3-ring chronology and climate variable, while at the same time controlling for the so-called secondary effects. So why is this important? Because in dendroclimatology, we usually have some temperature-related variables, and then we have some moisture-related variables like precipitation or soil moisture or water pressure deficit, and so on. And it can happen that because temperature and precipitation are almost always related. Meaning, if today it's very hot, there is no precipitation. When there is precipitation, it's usually a little bit colder. So if you analyze the correlation between temperature and moisture variables, you will very likely get significant correlations. I once calculated those and it was around 0.5. Okay, this is quite significant. And that's why I think partial correlations are very beneficial, because it prevents us to make false conclusions. For example, for primary climate variable like temperatures, we would say, yeah, there is negative effect of temperatures, but actually this would be the effect of precipitation, like direct effect. So that's why partial correlations are very beneficial, because we can exclude the effect of second climate variable. And this is done for monthly data in the C-score, and also for the daily data, it can now be done in the daily response C-score. So the function is pretty much the same. So the arguments are the same. The only difference is that you do not have a method, because method is already defined. You cannot apply linear regression. You can only apply partial correlation coefficients. So you can select P-core method. This is Person, Sperman, and Kendall. You have to provide 2 environmental data frames. So we have environmental data primary, and then we also have environmental data control. Like here, in this case, in the exercises we will do later, we have temperatures, and then we have precipitation as controlling variable. So we are going to exclude the indirect effect of precipitation on temperature. And of course, then we also need 2 aggregate functions. So function environmental data primary and environmental data control. Again, the selection of this will not affect calculated partial correlation coefficients, but it will affect the aggregated values, which are then given by the optimized output. Okay, so that's everything what I wanted to say about the partial correlation coefficients. We will now first check the bootstrap, and then we are going to check the partial correlation examples. So I hope this is, it's not finished yet. Okay, then we will still wait, and we will continue with next slides, which are related to monthly response function. So because I cannot run two parallel codes. I could, but it's not so important. So I will now explain you also about the monthly response function, and then we will go to exercises, and we will finish the bootstrap and the partial correlations, and then the monthly correlations exercises. So the monthly response function, you will see that we have monthly response and monthly response z-score. So again, monthly response z-score is designed to study the partial correlation coefficients between 3-ring chronology and monthly climate data. So this is the same as done with triclim and z-score from Dave Miko. So the monthly response is slightly different. So the lower and upper limits are not given in days, but are given in months. So the lower limit is usually 1, while the upper limit is usually 12. And all the other arguments are completely the same. Okay, so we have environmental data which needs to be given in monthly scale, naturally. So we need 12 columns, not 366, but 12. And again, we have the years given as row names. So we have discussed this: alpha, remove insignificant, previous year, aggregate function is the same as for the daily response. Okay, and again, if we now finish with the monthly response, z-score, you have 2 additional arguments: environmental data primary. This has to be, of course, 12 months, and environmental data control, secondary variable or controlling variable, as you wish, is given again in monthly scales. And of course, the aggregation function, because aggregation function has to be specified for environmental data primary and environmental data control, because we are also going to aggregate months into, let's say, seasons. So June, July, May, June, July, and so on. So that's why we also need to specify how are we going to aggregate different months into seasonal values. Okay, so now there are a lot of examples waiting for us. I hope that the boot is finished. Okay, it's not finished. Okay, so I will do this a little bit. I will do one trick here. Just a second. So I can work with 2 R sessions at the same time. So okay, so if you would like to work with 2 R sessions at the same time, all you need to do is just copy like R project icon in the folder, and then you can open 2 R sessions at the same time. So otherwise, I don't know how this would how this would go. Okay. So I will now open exercise number 3, and first we are going to do some exercises related to daily response z-score. So partial correlations with daily response. So we have just one simple example. Again, we are going to use suite 272 data, which needs to be transformed using the data transform function. But now we also need precipitation. So we will open suite 272 daily precipitation, and again transform this into appropriate data frame using the data transform. So we have, you can see here, 2 data frames, 70 observations, 366 variables. And now, just because I would like to later compare it, I will run first simple correlations. So using the daily response. And after this is over, I will also apply partial correlation. So daily response Z-score when I use environmental data primary temperatures, environmental data control precipitation. Don't forget about row name subset. Okay. So.
Järne, you have one question on Q&A.
Excellent. This is good timing. The bootstrap, yes, boot equals 1,000. So, yeah, so the number of bootstrap samples, I would say there is no such thing as the best, but I would say, so if you will use too low, then your confidence intervals are going to be very wide, okay? So if you are going to use too high, your confidence intervals will also be more narrow, but this function will take, very long to execute. So my suggestion is use 1,000, which in my opinion, it's enough that you get very nicely distributed correlations, which can then be used to estimate the uncertainty related with this correlation coefficient. So if any one of you has an idea what is the best N selection, please write this in the chat. Yes, but I think I always use 1,000 and never got any complaint by reviewers. So this would be my answer. Thanks. Okay, so simple correlations are now calculated. Let's also run the Z-score. So Z-score is a little bit, yes, thank you. Z-score is a little bit slower because calculating the partial correlation coefficients, it's slightly more time consuming and slightly more complex than calculating simple correlations. So this will take, and let's now check the bootstrap examples. The bootstrap example, it's only one. Okay, not this one. Okay, okay, so the bootstrap almost finished, but what you can see now, we have used only narrow selection, like from 50 till 67, but still it took maybe 10 minutes, and just for one example. So in case you are applying this on large, using more possible windows, this can really take long. Okay, so let's see now. Now we are back to bootstrap example. So the summary, what is now different than before? You can see that we are getting the confidence interval for this calculated correlation coefficient. It's very similar to what we have calculated using simple correlations, because if you can recall, using simple correlations, it was 407, now it's 413. So if we round this to two decimal places, we get exactly the same estimate. That's why I also, in this paper published in Quaternary Science Reviews, I have stated that using the bootstrap actually doesn't get you more accurate mean value, but you will only get the uncertainty estimate, right? So if you are not going to analyze the uncertainty, in my opinion, it doesn't make sense to apply the bootstrap because this value will be more or less the same. So, but this is up to you to decide. So I just want to say that the results are very much the same. Now we have June 19, before we had June 18, and here is August 16, which I think was also before August 16. So the optimal time window length, it's now 59, before it was 60. So pretty much the same results. But this is just an example. So if you would like to use the bootstrap, it's available, and feel free to do it. Okay, so now let's go back to exercise number 3. Okay, so we have calculated using the same data 2 types of correlations. First, simple correlation, then partial correlations. Now we are going to plot this, and as you can see, I would like to use ggplot2 syntax and the scale fill gradient to make it more comparable. So first open the library. Right. So first, we have already seen this before. This is the correlation coefficient. Simple correlations, we have the highest correlations between June 18, August 16, and we also get the significant negative effect from the end of growing season, right? Which would mean if there is a cold end of growing season, we get slightly narrower tree rings. But now let's see what is the result if we use partial correlations. So very similar. We again have the positive correlations with summer, but we do not get this negative effect arising from the end of growing season. So now it's really, let's say, up to you to decide which are more correct. But from my knowledge, if using partial correlation coefficients and getting no negative effect here at the end of growing season, this probably means that this effect is actually more related to precipitation. Okay, so we will not now go to analyze this and investigate why this happened, because the point of the webinar is to show you the functionality of the functions. But you can explore this, and maybe the idea for you in the future work, I think that partial correlations should be more often considered in dendroclimatological studies. So let's see this again. So this is partial, and this is the simple correlations. So we have here more significant values, which are also slightly higher, and also we get this negative effect. While for for partial correlations, we get slightly lower correlations, because the effect of precipitation is excluded. Okay, so now let's see the summary for both options. Okay, so I will run this again. Okay, so if we take a look at the summary for simple correlations, we get the information about the correlation coefficient here. We can see that here we have partial correlation coefficients, and the highest correlation coefficient was calculated using not slightly, but actually quite different time window, July 18, August 17. While here we have June 18, August 16. So, and this effect here is also much more narrow. We have it, the optimal window is 31 days. But in this case, we have 60 days. So again, this is not me to decide which method is better. I usually use partial correlation coefficients, at least in my recent studies. But yes, so it's up to you. You are free to decide to use any of those two functions. And you can also see that the values here are slightly lower. And as far as I know, partial correlations will always be slightly lower than, let's say, simple correlations, because you extract, let's say, the probable effect of controlling variable and get, let's say, a raw effect of chronology of primary variable, in this case temperatures. Okay, so we are now going to monthly examples, and then we have just 2 more slides and 2 more examples, and we will and then we are done. Those exercises now are shorter. Okay, so I will close. Excellent. Okay, so exercise 4 is designed and very important because we are going to compare daily and monthly correlations, also using monthly response, daily response. And I think if you are not convinced yet about the benefit of using daily data, then after this exercise, you definitely will be. I hope so. So let's empty the environment. We will just, okay, like before, open the library and now open the data suite 272. Again, so we are going to open temperatures, transform those into daily format using, so we are going to transform those first into monthly format. So the data transform function has also the argument format, and if you specify this as monthly, so the output of this function is going to be in monthly scale. Of course, you have to also specify how to aggregate daily data into monthly, but you can simply set this as auto. So this is like automatic, because based on number of zeros, it's very easy to estimate whether this is precipitation or whether this is temperature data. So the algorithm will automatically see whether you have temperature data and use mean, or if you have precipitation data with zeros, and it will summarize. So you will get the sum of monthly temperatures. Okay, so let's run this. Okay, so we have now, let's see, one data frame for monthly precipitation. We have 12 columns. Those are sums of monthly precipitation, and row names are specified as years. Let's see also temperature table. So the algorithm correctly realized that we are working with temperature. So those temperatures are summarized. So we have mean monthly temperatures for different years. Okay, so let's simply calculate the correlations between our response chronology and our temperatures. This is very quickly because the windows are, yeah, we have just 12 columns, and we just aggregate this using the lower and upper limits, which are here by default 1 and 12. So let's see the summary of the simple correlation monthly. So we have monthly approach. So this is important for you to know. Then we have correlation coefficient, analyzed years, and the highest calculated metric, in this case correlation, is 0.29 and something more. So if we go back to what we had before, it was 0.4. And now the highest calculated correlations, considering all possible windows, also 3 months, 3 consecutive months, 6 consecutive months, 7, 8, and 12 consecutive months, we have only, yeah, I would say pretty much lower and only, yeah, let's say, yeah, okay, so you know that I am a fan of daily data, so I will now promote the daily response function. But as always, I will say that it's up to you to decide which is for you more convenient. Sometimes, you know, daily data is simply not available, or it's of too low quality, and of course, then you will apply a monthly approach. But in terms of correlations, you will probably find more significant correlations using the daily approach. So we also get the information about the optimal time window. In this case, this is July, a single month. Okay, and so the starting month of optimal window width is month 7. So we have only 7. This is July, and if we combine different months, we cannot improve this correlation. So plot, okay, so let's see the plot. So we have...
Sorry, Jarni, you have one question?
Absolutely. So it's a question. Hi, Katalin. So can we insert the previous year in the monthly? Like, yes, of course, we can. Let's do it actually. So previous year. So previous year equals true. Ah, okay, this is the next example. Let's go back here. Okay, so let's see the summary. Okay, so now thank you actually for this question, because it's now the results are much better now. So, but we see that this effect of previous, it's more prevailing. So the correlation now it's 0.43. If you can recall from the example related to daily data, this correlation was 0.48. So it's still more significant for daily approach, but at the end, also this effect of previous year here, it's more pronounced and more significant than before. So yes, you can simply add the previous year equals true, and now you will get the effect of previous year. And so those asterisks related to previous year, this is commonly used in publications. And we have now, okay, we now have 2 consecutive months. So September, October, yeah. So number 9, this is September, plus 1 plus, yes, so September plus October, we have these 2 months. Excellent. Well, okay, let's see now this plot of simple correlations. So of course we have now more, before we had just this, but now we see that this previous growing season effect is very pronounced in this case. But just I would like to say that in the bottom row, we have only single months. So January, this is starting at the beginning of previous growing season. So January, February, March, and so on. And now we have the effect of current growing season, January, February, March, and so on. And then in the next row, we have 2 consecutive months. So this is January, February. This is February, March, March, April, April, May, May, June, and so on. Okay. Now, for example, here we have 10 consecutive months. So in this case, this is from January till October from the previous growing season. February till October from the previous growing season. Because in this case, the x-axis always indicates the starting month of calculation. And now you also get the information including previous year. So you know what is going on behind this. And so I think that the maximum number of consecutive months is 12. I have tested this and try to increase this, so we could also, for example, use 24. But I think there were some problems with the calculations, and then I did not complete this. But let me see if this is maybe working. So if I have the upper limit equals 24. Okay, yeah, so this is working. Yeah, okay, so now you get actually the effect of 2 consecutive years. So this is the, for example, this 24, this is the aggregated data starting in January from the previous year till December of current year. So of course, this is non-significant. And you can also see that this effect having more than 12 always yields non-significant correlations, which makes me happy because usually those effects are more narrow, at least in my experience, maybe a few months, 2-3 months, something from previous growing season and some months in current growing season. So, okay, I think that the next exercise is related to monthly response Z-score. Let's run this. Okay, and yeah, again, so this is the same as implemented in the TreeClimR package and in the Z-score from Dave Miko. Let's see the summary. So what we have here is the monthly approach. In this case, because we did not consider the previous year, this value is even lower than before. So Okay, to be more fair, I will now use the previous year equals true. Okay, so this is monthly response. Okay, great. I was afraid. But yes, okay. So again, we have the effect, which is the most pronounced from previous growing season, end of growing season, and partial correlation coefficients, which the highest value was 36.2. Okay, so that's the last question, but we have already answered this. What is the benefit of using daily data? So I will just repeat this simple correlation again, because I wanted to compare correlation daily and correlation monthly. Also, but for monthly, then we change this for previous year, so this is not directly comparable. But again, so the highest calculated correlation using simple correlations and only current growing season was 29.5, so 0.29 and something more, while using the daily data it was 0.41. So there is let's say a difference in terms of 0.1 in terms of correlation coefficients. If we use partial correlation coefficients, still the difference is slightly lower, but still we get more significant results using the daily data in comparison to monthly data. So, okay, I think that now we have finished with the exercise number 4. And we have only one exercise more. Let me see what are on the slides. Yeah, okay, on the slides. So we have only one exercise more. And this is exercise number 5, where I would like to show you a very simple procedure and just a few steps how to use the dendrotools to reconstruct climate. So this is going to be just demonstrative example, so that you can see how this is possible. But the data which I'm using, this suite 272, is not optimal for climate reconstruction because the correlations are, not so high, not so significant. But just for the sake of demonstration, we will now accept this as our example. Okay. Okay, so again, the beginning is always the same. We are going to reconstruct temperatures using daily response function, and we are going to first identify the optimal climate signal. We already know this is from June 16, August 18, and then we are going to use the this optimized return to calibrate the model and to see what we get if we just simply develop a linear model, and then what we get if we develop non-linear model, and what are the differences between two. And yes, I think it's going to be interesting. So now I'm running this probably for the 5th time today. Correlation run, daily response. We are using the method equals correlation, and we are going to use the running window as temporal stability check. So first, let's see the output. Again, so we have the highest and the optimal climate signal calculated from June 18, August 16. And if we now would like to see how this is stable in time, this was already shown on slides before. So this is different data than from the slides. So we can see that correlations using sub-periods are, actually here we have a huge drop in correlations. So we are getting to non-significant correlations. So again, please don't use this data for climate reconstruction, but just follow the procedure. So I'm not sure now whether we could go back and maybe see if we can improve the standardization. Maybe the trees are just were under stress or something. So this data is not optimal for climate reconstruction, but we will still use it to show you the procedure. Okay, So the transfer function between optimized return in this case and proxy. So this is actually our linear model. You can see there is huge uncertainty around it. You can see some, so those are the expected values and those are the scattered values. So it's a huge variability. Again, but for now, let's accept it. We should also see the temporal stability. Okay, correlations, if we compare early and late period, slightly drop, but this is not so drastic. Using those subsets, we have seen before that if we use running window, they significantly drop. And again, so reduction of error and coefficient of efficiency are negative. So forget about climate reconstruction here, especially, coefficient of efficiency is negative. The only potentially acceptable value would be this one. So just that you know that, yes, that is not the optimal, but let's continue just for the sake of demonstration. So I will now use this optimized return. I have explained before what is this. So in optimized return, this is a data frame with two columns. In one column, we get our tree-ring width chronology, of course, standardized. And in the other column, there is optimized return. This is aggregated data from the optimal time window. This is, in this case, June 16, August 18. Okay, and now we're just going to change the column name because this is more convenient for the plotting purposes. And I will apply linear model. So in R, if you know R, then you probably know the LM function, which is going to fit linear model between our response and our optimized return. And the data which is used to do so is simply the optimized return from the our example. We can see the summary of linear model. The variable is significant, but as we have seen before, not really optimal for climate reconstruction. So now we are just going to use the predict function. So in the predict function, we insert LM, so a linear model, and then this is data which is used for prediction. So we are going to use our suite 272 chronology, and using those values as independent variable, we are going to predict. So June, August, so June 16, August 18, temperature in this case, okay? And for the plotting purposes, we are going to add another column. This is year. Okay, let's open the ggplot, and here we go with the first reconstruction. It's very simple, as I said. So we have here the predicted values for the recent period. This is also where we have data available, but using this long chronology, we can cut this, we can reconstruct this back in time. So we should analyze so-called EPS, so express population signal, to see where is the sample size high enough to present population, but we haven't done this. But if you decide to use this for climate reconstruction, please make sure to do all the necessary steps which are usually applied in the climate reconstruction process. Now I would like to add another line, and this line will be predicted using the BRN method. So to do so, we are now going to use the BRNN package and first simply feed the model. So as you can see, the only difference between linear and non-linear regression in this case is just the LM versus BRNN. Okay, so the syntax is the same. And now we are going to use predict. And as the first argument is our nonlinear model. And then again, we will use the suite 272 chronology for the prediction. Okay, we will add this prediction to our reconstruction data frame. So this is our table. Oops, And if let's see. Okay, so this is our table, and in this table we have a linear reconstruction. Okay, this is year, and we have non-linear reconstruction. Okay, now I will just transform this table using the melt function, because in ggplot you should always work with so-called tidy data. So what is tidy data? So in data science and in general in data analysis, we distinguish two types of data. So first is so-called tidy, and then we talk about the untidy. So untidy is what we see now. So different variables are in separate columns, but with tidy, then we have value described with variables. Okay, you will see the difference in a moment. So we would like to have a special column, which is, for example, method, and then we have another column with the value. So with the method, we describe which method was used for the prediction, and with the value, we actually specify the prediction value for a specific year.
Okay. So you have one comment in the Q&A.
Okay, thank you very much. Thank you, Katalin. So maybe the scale method is proper in this case. In this way, we will avoid the variance losses induced by regression. Yes, okay, this is a good point. So, yes, the scale method would probably be sorry, better. But as I said, this is just a demonstration for now, but good point from Katalin. Okay, let's now finish this example. So we have predicted the switch to we have predicted the temperatures using the nonlinear model using the predict. So first feed the model, and then okay, we have already done this. Okay, and now to get the tidy data, we are going to use the melt function, which first we just have to specify which is our ID variable. In this case, those are years. Okay, first, before using the melt, we have to open the library of reshape2. Okay, so let's just see what is now this reconstruction data frame. Okay, so this is the difference. This is tidy data, which you need usually to plot in the ggplot. Okay, so we don't have separate columns for linear and non-linear reconstructions, but we have one column specifying the method. Here we have linear, and down there we have non-linear. Yes, and always we get the description for the prediction from the value column. Okay, and if I now, so what we have to do here is assign variable as color, so we will get two separate lines. Okay, so now we are plotting two separate climate reconstructions, one with linear and one with non-linear model. Looks pretty similar, right? So as I said before, the difference between those two methods is mostly related to extremes. In this case, especially narrow extremes. So you can see that the down there linear method, which is red color, for the extreme years has, let's say, more extreme predictions, while non-linear method has less extreme predictions. So now it's totally up to you. If you have any thoughts, please write them in the chat or answer in questions. What do you think? But for me as a forester, when we studied how trees grow, and for me, it's more likely than trees in those extreme parts of climate growth relationships will not respond, in the same context as in this central part of climate growth relationship. But I hope this discussion is going to evolve in the future. So, and maybe we will also we will be reconstructing climate using non-linear methods. Well, okay. So there in the slides, there are I have already shown this. You have seen the differences in extreme predictions. You can also see this is the difference in transfer functions. So this is linear transfer function and this is non-linear transfer function. You can see that they are more or less the same. Only what we have here is this function is when it goes into the extreme part of into the extreme narrow proxy, it will have less extreme predictions like this function, which goes down here. Yes. Okay, so this was the last example which we are going today. And the last thing in this webinar, I have prepared a homework for you. Because this is one topic which was not covered and was also not meant today. But a few days ago, I received a question about the daily SPAY and daily correlations in dendrotools. And I have prepared one example which will be sent to you after the workshop, because I have to add some comments. So I have prepared example which is you will get the folder. So just a second. Yes. So okay, you will get this folder, daily SPAY example. And in this daily SPAY, you have a running example how to calculate first the difference between potential evapotranspiration and actual precipitation, and then how to apply this calculated variable in daily response. But this is not actually daily response, because the way how SPAY is used and aggregated is not fit for the daily response. Where is the problem? So in the daily response, we have a fixed data which starts on January 1st. But to use daily SPAY, we cannot fix and prepare our data using the January 1st. So data preparation is totally different, and it's included in this step 2 process. So please study this at home. Probably we will cover this in the future webinars and workshops related to dendrotools. But for now, just in case you're interested, please take a look and use SPAY step 1 and step 2. This is running example, so all you have to do is maybe change the climate data and the chronology, and then you can apply this on your data if you need to calculate daily correlations. So we have now finished with all the content that I had planned. If there are any question, any thought on anything, I think we can still use some time, and I can answer any questions. There were quite some questions already during the workshop, so I think it was very interesting, and I think it was the right way that you ask your questions and interrupted me. I think this is better, because otherwise we would now need to go back at the beginning and some things which are not so fresh anymore. But if there are no questions, so this was actually quite long. It took 1 hour longer than I thought. So, but thanks for everyone who stayed by the end. I already have received some emails. I will try to answer all of you in the next days during the conference, and then maybe in the next week. So yes, thank you as well. And you will receive this SPAY example today in the evening or tomorrow during the conference. I am very looking forward to. I hope that all the complete workshop will be available soon. I have to speak with Alan to put this. And thank you, everyone. Enjoy the evening, and thank you, Diogo, for staying and helping me with the questions and answers. It was really helpful. I hope that you got a lot of useful information. And take care and see you during the conference. And if you will have any questions related to dendrotools or any other subject, you can always write to me. I usually respond within a few days. So thank you very much. Yes, thanks for nice comments in the chat, and have a nice time. Take care. Bye-bye.